Welcome everyone. In this video I'm going to continue my CH32 tutorial series, and I continue what I did in the previous video where I showed some basic GPIO manipulation. So in that video I showed you that if you open the default project, you will already get some kind of USART code which is capable of communicating with the computer. So this video's topic will be the basic USART communication. So as I said, one reason why I picked this topic as the second part of this series is because I have already touched this topic a little bit, but then it will be also useful in the upcoming projects. For example, later on we can send commands to the microcontroller to start or stop sampling with the ADC, or we can receive data from other sensors and so on and so on. And we can also communicate with the microcontroller in different ways. So we have the empty development environment here. So let's create a new project. So I just simply go to File, New, and Project. And again, we select the corresponding microcontroller. So that's nice. And then we give some name to the project. So this will be part 2 USART. So that's done. So again, I closed all the unnecessary windows such as the Project Explorer and so on, and I have the source code shown here with somewhat larger characters, so hopefully you can see this properly. And as I mentioned in the beginning of the video, the example code already has the USART code implemented, so we will base our tutorial in this already existing code. And just as a reminder, why we are using USART is because the chip doesn't have any native USB. So we need a USB to USART converter, and that is actually the programmer. The programmer has this function that can convert the RX and TX pins into USB communication. And then we can communicate back and forth with the microcontroller via or through the programmer. We have this config for the USART, and this doesn't need any kind of explanation. Maybe one thing that's worth mentioning is that the baud rate is this 115200. This is a very typical speed, and a very typical mistake for people who start working with microcontrollers and serial communication is that they set this value to a certain value on their device. Like here I set it to this highlighted value, but on their serial terminal they do not select another value than the default value, which is typically 9600. And if the two baud rates differ, so on, let's say, receiving and sending side, they are different, then on the receiving side and also on the sending side, but what you see is on the receiving side, so there you will receive garbage characters because of the different baud rates. So make sure that you have the same exact baud rate on both sides. So let's go to the main loop, and first in the quote-unquote setup part, let's weed out the code a little bit just to have something nice like that. And let's do a printf to send something on the serial terminal after we started the microcontroller. Actually, we can add the delay here. So after resetting the microcontroller, after we programmed it, we have some time to open up the terminal and catch up with the stuff and actually see the message as a wall. And here I want to just delete this part. And let's implement a very simple function, an echo function, which will receive a character from the serial terminal on the PC. So we will send a character to the microcontroller, and then the microcontroller will send it back. So let's open another function. We will call it like this. And then let's see if we can receive. So what this means is that if this flag on the USART is set, as you can see it in the briefing here, then we can enter this block. And then let's create a variable. I just write it down. And let's create this up in the beginning where we have the global variables. So I just delete this. And let's call it a char and receive data. And I don't declare it with any kind of values, but I just write a comment there. So if you go back to the function, then this is what we need. And then we need to also send it back, because this is just the receiving. It will look like this. And this is the raw sending and receiving. So there is no scanf or printf or similar functions. So this literally just checks the flag. We will put it in the loop, in the infinite loop. So it will poll the USART. And whenever the flag changes on the USART, that means that the character arrived to the microcontroller. And then we kind of pass that character to the received data variable. And then we send back that received data variable to the same USART port. So that's that. And then, as I said, this has to go here. So now let me do this 5 seconds. So I compile this. It went well. And I send it to the microcontroller by pressing F8. So here is our terminal. And this is fine. So now we got the message, which is right here. And I just send the character. And I need to change the settings of my terminal. So what I need to do is I need to put this in line mode there. So then I can type here, let's say a capital A, and then it's E-code back to us. And if I send capital or small t, then it's sent back to us, or R, it's there. So it works. I can send multiple, because each character is read and immediately sent back. So even if I send a string, like literally a string, then it will appear as a string. Now I talk about the type, because we just rapidly sent back the individual characters. But this is not a string. This is basically 6 characters. How we can make sure that it does what it does is that, for example, I send a character, and if you look at the TX, RX, let's say, status lights, they will both blink. And if it was just a unidirectional communication, only one, let's say, light would show up. But you see that both blinks. So this works. So this is just that we can establish some kind of communication. But let's put this function aside, so we don't need this. And let's make the next function. So just for a moment, if you look at our board, I just magnify it. So here is the module, and then we have the microcontroller, same as the previous tutorial. We have the LEDs and the 4 buttons. So why not do something with these, let's say, devices, like LEDs and buttons, and the USART. So let's make this thing to toggle individual LEDs when I send a character from the serial port. So I send, let's say, 1, 2, 3, and 4 numbers, and then it will show or light up the LED 1, 2, 3, and 4. I think that would be nice. So let's do that. So let's develop another function, and we will call it toggle LED USART. And let's use the switch case block. So it will be based on the received data. And then we develop 4 cases. So actually these will be the characters which will switch certain LEDs. And then we have to first declare the pins as outputs, because that doesn't exist yet. So I just go into this function, where we already have the TX and RX pins, and I will just declare 4 pins for the LEDs. So if we remember from the previous example, then the LEDs were located on the GPIO-D port mostly. So PD0, PD2 and PD3 pins, that's still the same. And then there was another LED on PC1. So what I can do here is that I can add the C port to this clock configuration part. So that's done. So now we can reach the C port. And then we need basically these 4 lines. And we will need to modify them just a little bit. So as I said, on port D, we have 0. And then we can combine this with pin number 2 and pin number 3. So that's fine. Speed is okay. And then here we have a push-pull output, and that is on the D. So that's fine. And then I copy-paste this again and put it here. And now we need to do the same or similar for port C. But on port C, we just have 1 pin, which is pin number 1. So I just separate them a little bit. So these are the LED pins in this block. So PD0, PD2 and PD3 and PC1. So that's fine. So we can go back to the toggle function. And then if you remember, we have something like this. We have to write a bit on the corresponding GPIO. So we start with GPIO D and we have the pin 0. And then, since we toggle, we do the same kind of exercise as we did in the previous lecture, which is that I read the bit value which is currently stored in the register. So GPIO and read output data bit and on the same pin. So port D, pin 0. And then I check if this is bit set. And if it's set, then I reset it. Otherwise, if it's reset, then I set it. And then that's all. And just for fun, I add a little delay. Still, we haven't learned how to do, let's say, non-blocking stuff, coding. I will show you in a further tutorial. So here we just block, and just for 10 milliseconds. So this is fine. And now again, I just copy paste this a bunch of times. And then we agreed that we have a GPIO C1. So let me do that. And we have a GPIO D2 and GPIO D3. So that's fine. And now this function should go here because it should kind of poll the USART. However, when I removed this function, I also removed the part here where we pass the character received from the USART port to the received data function. So what I'm going to do now here is very simple. I remove this and place it here. And we don't need to send it back. So now each time when this function is called, we poll the USART port and check for the RX status. And if the RX is set, then we kind of pass the value to the received data. And then if that value is 1, 2, 3, or 4, we will toggle the corresponding pins. So let me see if this compiles now. It does. So I can send it to the microcontroller. Let's open the terminal. So that we have there. And let me show you the camera, so you also see the LEDs if they are toggled or not. So I'm sending now number 1, and it is toggled. I send it again, switched off. Number 2, there you go, number 3 and number 4. And if I send something else, then the LEDs are not changed. So once again, 1, 2, 3, and 4, and 1. So this works. This was easy. So now we know how to send a command basically to the microcontroller and make the microcontroller to perform something. And of course this in the future will be very useful, because you can build like a similar switch case scenario where you basically receive a character and then you parse that character, and you can see that, okay, if this character is a certain character that you pre-programmed, let's say the number 1, then we do something. You can put here a function, you can put here anything that you want, and then that will be performed. So that's very nice. So now you learned this part as well. So as a next step, we could do this backwards. And what I mean by that is that now instead of sending an instruction to the microcontroller to do something, we do something with the microcontroller, and it will send back something to the terminal of the PC, to the serial terminal. And since I showed you that we have 4 buttons, let's do something with those 4 buttons. So let's implement another function. And what we need to do here is very simple again. So we just read the input data bit of the selected GPIO. And let's say this will be GPIO C and pin 0. And then we check if its value is bit reset. And if it is, then let's say we printf that the button 1 was pressed. And now I have to explain you what happened here. So we just read the input data bit, that is the bit of the port that was like manipulated, and we do it on the C0 or PC0 pin. And we check for reset because, as I showed you in the previous example as well, the buttons are pulled up to the supply voltage by a pull-up resistor. So when the button is not pressed, like right now, then the button's status is high or set, so bit underscore set. And when you press the button, then that circuit is shorted to ground and it will be pulled down. So then the input data bit of this specific C0 pin will be bit underscore reset or low. So then this becomes true. So then we can proceed further and send something to the serial terminal. And similarly to the LED pins, first we have to declare these pins as inputs. So let me go back here, and we have button pins. And then let's cheat again. So I take this, copy paste, formatting, and then how I declared the buttons is that I have a GPIO pin 0, and then I have GPIO pin 2, GPIO pin 3, and GPIO pin 4, and they can be found on the C port, that's fine, but their mode is input and floating. And why it is floating is because the chip itself doesn't have to set a pull up or pull down resistor, but it is left floating, and what puts it in a determined status is the external pull-up resistor which is connected to the button and also to the GPIO pin. So this is done. So we can go back here and just write 3 more of this and modify this. And then we agreed that this will be pin 2, pin 3 and pin 4. And since the button tends to bounce, then I do a performance debounce. And what this does actually is just that after one of the pins status is red, the code gets stuck here for 100 milliseconds. So actually it is not able to read the status of the GPIO port or pin for 100 milliseconds. And that 100 milliseconds is enough for the bouncing to decay. So then when next time after 100 milliseconds the code returns to this part, to this function, it will not detect the bouncing, or in ideal case it will not detect it. So let's fancy up the code by some formatting and then copy paste again. I can leave this here, I don't need it, so I can just compile and send it to the microcontroller. So terminal is up, we received the message, and let me show you the buttons. So we have that, and now I press a button. Button 1 was pressed, button 2 was pressed, button 3 was pressed, and button 4 was pressed. So yeah, this works. Here actually you could see a bounce because the same number was printed twice. So the delay, that 100 milliseconds delay up here, that was not enough. So maybe we can put there 200 milliseconds or even more if it's not a time critical code. But yeah, it works. So now we can toggle an LED or multiple LEDs and also receive, let's say, information from the GPIO ports. But let's do something more complex, because yeah, we can turn on or turn off an LED individually, but I want to specifically tell the microcontroller that now I want to switch an LED. And why I want to do this is because, for example, I can recall an old example. I worked with a chip which has registers, and then I can, let's say, read those registers, like reading it, reading the first register, the second register, and so on. But I can also write those registers, the same number, 1, 2, 3, 4. And then how do I distinguish between them? So one thing could be that, for example, I send the command R1, R2, R3 to the microcontroller to read the first, second, and third register. And then I can also send W1, W2, W3 to the microcontroller to write the first, second, and third register. So we can develop a kind of an algorithm or a small piece of code which can recognize that we have a, let's call it, command character, and then based on the command character it can also decide what it should do with the rest of the characters. So let's do that. So again, another function. So this function actually has a command buffer parameter. So let me just declare this. Let's say size of 10 will be enough. So this buffer actually only just holds 9 characters and not 10, but you have to declare it like this because the last item is always a no terminate item. So that's why it's 10 minus 1. So let's get back to the function, and we need to know where we are in the buffer, like which item number. So I just do this, and let's call it index, and this will be 0. And then we have a received character, which will be extracted from the received buffer. And first we want to clear this buffer. So we take this buffer, fill it up with zeros, and we need 10 zeros in it. So all the items are deleted. So this is just a simple array resetting function, let's call it like that. And then what we do is we write a while loop here. So we go basically up to 9, and that is because of the no terminate character. And then we keep receiving stuff from the USART, from the USART 1, and we need the RX flag, and we look for the reset. So we wait for this flag, so the code gets stuck in this line. So we wait until it goes to set, because as long as it is reset, then the code waits in this line, but when it goes to reset, then it will proceed. So then the received character will be the received data from USART 1. And this is just one character at a time. And what we do here is, let's do it like this. So if the received character is, let's say, an endline character, or, so this is a logical or, if the received character is this other type of endline, then we don't continue doing our stuff, so we break. So this jumps out from the wall while. It jumps out from this, and it will end up in this line here. Otherwise, the code proceeds, so it will be here, and we can add a new item to the comment buffer. So with the new index, we can do this. So once again, we go up to maximum 9 characters. First we wait until the status, the flag, goes to set. The code is stuck here until as long as the status is reset. So after it goes to set, the code jumps to this line, and it passes the character received from the USART to the received character variable. And then it checks if this received character was an endline character, and if it was, then we jump out from this wall stuff. Otherwise, this will be performed. Actually, I mean, if we are very, very meticulous here, we can do like this. It's no big deal. Doesn't matter in this case. But we can do this. So if it was not an endline character, then it means that it was a valid character. Therefore, we need to put the stuff in the comment buffer array. And then we reach the end of the while. So then we have to finish the comment buffer. And that will be with the index. And that should be the null terminate character. Something like this. So this is basically done. And now we have to process this. So we need another function. So first of all, we need to pass the command. And then we do like this. So we check if the command 0 was a capital L as LED, and the command is at least 2 characters long. Then we start to implement the inside of the if block. So let's do this. So we have a character which will be the command number, and that is actually the second item, so item number 1 in the command buffer. And then I do a cheating ASCII to integer conversion here. Actually, this line might need some explanation, because I think this is a very, let's say, elegant stuff. So the characters are represented using their ASCII values when you send them on the terminal. So for example, if you send the number 0 on the terminal, then the ASCII value of it will be 48. The number 1 will be 49, the number 2 will be 50, and so on and so on. So actually, when we subtract this 0 character from whatever received ASCII number we had, then we actually convert it into integer, because yeah, as I said, the number 2 is 50 in, let's say, ASCII code, and if you subtract the 0, like the number character, like the character which has the ASCII value integer of 48, so 50 minus 48 will be 2, and that 2 is stored as an integer, and that's the legit number 2. So this is how it works. And then we do like this. So if this index is larger than 1 and smaller or less and equal than 4, so we have a number received between 1 and 4, basically, that's what this means. Then we do something. And now I go back to my previous code, which is this guy here, and I copy paste and put it here. And the only thing that I have to change here is this guy here. And then they become, instead of characters, they become numbers. And I don't need a delay here, I assume. So let's do it like this. So just a little recap what we did here. So when this function runs, it checks the content of the buffer that we built by receiving, let's say, a string of characters on the serial terminal, which was built in this function up here. And then if the first character, so the character at the 0 index, is a capital L, and the whole command is longer than 2 characters, then we further proceed and pass the second character, so item number 1, to the command number. And then that is still a character, so we convert it by subtracting the 0 character from the character that we actually have. And due to the logic behind how the ASCII characters represent the actual integer numbers, we will get the integer value here. And then we check if that integer number is between 1 and 4, because we have the LEDs between 1 and 4. Then we further proceed, and based on this command index, which should be 3 and 4 here, we toggle one of the LEDs. So let's put the functions where they belong. I remove these to avoid any confusion. And this guy will have the command buffer. And this guy will have the command buffer as well. So let me compile. And I made a mistake somewhere because the compilation was unsuccessful, and it's a very, let's say, beginner mistake. So this is finished. So let's send it to the microcontroller. So this is fine. We received a new line. So let's look at the board as well. So now we are at the board. And let me send L1 to the microcontroller. And that is L1. L2, L3, and L4. So they both work. And I can just show you that, for example, L5 will not do anything because that's invalid. L will not do anything. And if I send the characters individually, that won't work either. So I have to send L1 together, or L3, or L2, or L4. So now we passed another, let's say, threshold again. We know how to send command to the microcontroller as a, let's say, string or string of characters. Maybe that's a more precise description. And now we are able to decompose that string of characters, and we can pick out our, let's say, command character, so we know what we want to do, and then the command number, which is basically that we know which feature or which GPIO port or which whatever we want to modify. So this is nice. And coming back to the code, we can actually modify this and make it work for the buttons as well. So I just copy paste this wall if block, which is hopefully this, and change it one by one. So now let's change this to B as button, and then the rest almost stays unchanged. So this is unchanged, unchanged. This is also unchanged. And then the command index should also be the same. However, I need to rewrite this line or these lines, all the four. So what I want to do here is, let's say, I need a new variable, pin status, and that will be simply just the read input data bit. And then we know that we have GPIO pin 0. And then I just rinse and repeat here, here, and also here. And then I change this to 2, 3, and 4. And you can see that here the compiler already highlights this because it's not described anywhere or declared. So I just go here, unsigned integer 8 is enough, and let's do it like this. In fact, let me remove this. Hopefully this won't confuse you, and I can do this. I put it right here because we don't need it globally. We just need it inside the function. Once this switch case block is finished, we can do like this. We check what is the pin status. If it is bit underscore set, that means that the pin is high. So then we can print that the whichever pin is high, and then do a line break. Or I can put an else block here as well. And then, of course, the else should say low. And then I forgot this. So this will be the command index, because that is the pin number in our case. So what this function does is very simple. So we have the pin status variable. And then if we send, let's say, B1 to the microcontroller, then actually it will go and check the PC0 pin, and it will put its status in the pin status variable. And when this is done, it will check what is the value of that pin status variable. And if it is set, then that is high, and that is the default in our case because the button is pulled up with a pull up resistor. Otherwise it is low. So let's compile this. So it compiles, and let's upload this. So terminal is there, but you might need to see this. So that's there. So now I send B1 and it's high, but I type this in, press down B1, and now B1 is low because I pressed the button, so I pulled it to ground. And B2 is high. I read it once again just to show you. But if I press the button, then it's low. And then B3 and B4 So it all works. And of course, it's not really probable that you would want to do this, like read the buttons so manually or so mechanically. But it can happen that you want to, let's say, read the status of a certain GPIO port like this, because it is modified by another device, an external sensor or a limit switch or whatever. So then you just want to check it from time to time. And then with this, you can send a command, and you can decide that you would like to read a certain GPIO port. And this is how you can do it. And with this, I think I finished this tutorial, because this was basically all that I wanted to say and wanted to share with you. Now, as a short summary, now we know how to send commands to the microcontroller, and then the microcontroller can perform something based on this command. We will utilize this a lot in the future tutorials. And now we also know how to, let's say, read, forcefully read some statuses from the microcontroller using commands again. And again, this is also very useful, and we will utilize this in the future. And also, we learned how to parse characters or string of characters, not strings, but just a series of characters coming from the serial to the microcontroller. And that is also very useful, because you can send like text to the microcontroller, and that will be useful when you want to print something on a display, for example, and things like that. So as usual, I put a lot of resources on my website, so please check the link in the description, because that will lead you to my website, where I have all the code snippets and extra resources and whatnot, so you will find everything there. And also visit the parts and tools section of my website, because you can find these development boards and everything. And you can also support me by actually buying those things via my links. And if you like these kind of topics, such as microcontrollers, programming, electronics, don't forget to subscribe to my channel. And also please consider signing up as a member. So I hope you like this video, I hope you learned something, and see you in the next video.